we are doing is we are breaking the input string into three parts, right? And we have given the name of the substring as U, V, W. So in the diagram we have, it is clear, the first part is U, the part that has been pumped is V, and rest of is W. So we are dividing the input string into three parts, U, V and W. And how we can divide it? There is a condition to divide it, and we are dividing it in such a way that the length of this substring UV must be less than or equal to n. Right? This is the precondition. And the length of this V must be greater than or equal to 1. So at least its length must be 1. Right? And for all I greater than or equal to 0. Then if these two conditions are satisfied and we are able to break the Z into three parts, then we are concluding that for all I greater than or equal to 0. So now we are finding the value of I also, right? Such that if we pump this V with I, it is again in N. Whatever the resulting string we are finding after pumping V, that will also be part of the accepted by the final. So furthermore, N is no more greater than. So what we are talking about, we are saying that the finite automata has N number of states. So those N number of states are smallest finite automata, minimized finite automata. So clear the definition? Any doubt in this definition? Because this is very important. Clear? So next, just write down the applications of pumping lemma. The pumping lemma is extremely useful. The pumping lemma is extremely useful in proving that certain sets are not regular. The general methodology in its application is an adversary argument of the following form. So what does this mean? So this pumping lemma for regular sets is always used in an adverse effect, in a negative way, right? So you will always be given a question that prove that this language is not regular. We cannot use it for proving it a regular. So we are using it in an adverse way, that you will be proving the given language is not regular, right? So what we have to do is, so we will be finding the value of I somehow, and when we are putting that value into the input string, that will violate it, that it will not become the part of the regular set. So we will then say that this is a contradiction and this is not a regular set, right? So we'll coming to the example, I'm just explaining that. So pumping lemma is always used in an adverse way, that will be proving that the given language is not a regular language. So write down the first point, select the language capital L. Select the language capital L you wish to prove non-regular. Select the language capital L you wish to prove non-regular. Second point, the adversary picks small n, the adversary picks small n, comma, the constant mentioned in the pumping lemma. The constant mentioned in the pumping lemma. Third, select a string small z. Select a string small z in capital L. Next point, the adversary breaks small z into u, comma v, comma w, comma, subject to the constraints that modulus of uv is less than or equal to n and modulus of v is greater than or equal to 1. Subject to these constraints. Modulus of uv is less than or equal to n and modulus of v is greater than or equal to 1. So next point, you achieve a contradiction to the pumping lemma by showing, comma, for any u, comma v and w, u, comma v and w determined by the adversary, comma, that there exists an small I, for which u v I w, for which u v raised to power I w is not in capital L, full stop. It may then be concluded that capital L is not regular. So all the points are clear? Right. So now lastly, we will be writing a formal statement of the pumping lemma. So it is simple to correlate with this definition. For all languages capital L, there exists small n for all strings Z. Z is in the language L, and the length of that Z is greater than or equal to N. This implies that there exists UVW such that we have broken Z into three parts UVW basis on this condition. And for all I, UVIW is in. So this is the formula. Right? Any doubt in it? Now we move forward to the example corresponding to the pumping lemma, and you need to be mentally prepared about that. Pumping lemma questions, examples, whatever is there. So there is a portion in each and every example that you have to grab. Right? So no doubt with very much experience we are able to do that by ourselves. Even I am not able to do without this cramming, right? So there is a portion in every example of the pumping lemma. You need to cram a portion over there, right? So finding the value of I, how to divide into three parts. So this is the portion that need to be crammed. So now we are starting with the first example. Prove that. Write down. Prove that So first of all, just think and let me know what type of strings are accepted by this language. Which are the strings that becomes the part of this? Double zero.
Even sorry. Double zeros and four zeros.
Single zero.
Single zero.
Single
So
zero.
I should be greater than equals to 1. 1 4 0. Then double zero is 4 zeros. So 1 4 9.
Double zero. Double zero will not be part. Double zero will not be part of this language.
Double zero is 0 for 4 times 0.
Then 9 times.
So in English, what we'll say? What type of strings are acceptable by you?
4 times.
Squares of the delta number.
The strings whose length is a perfect square. Right? So the strings that are made up of zeros and whose length is a perfect square. So now we have to prove that this is not a regular set. So how you start with that? So just see the points we have written in the applications of pumping lemma. So those points will be followed over here for solving it. So first is, so write down first point is assume capital L is regular, right? So we always start with the assumption that the given language is a regular language, then we will contradict it. Then what is the second point? Let N be the integer in the so that is your second point. Then we are selecting a string Z in the capital L. Let Z equal to 0 raised to power n square. So is the length of z greater than n or not? Because our condition in solving through pumping lemma is we have to choose the value of z whose length must be greater than n, greater than equal to n. So is the length of z greater than n or not? How many zeros are there in z? How many zeros are there in n? Z.
And square.
N square. N square is greater than n or not?
Yes, that is
So it means we have chosen the right z in which the length of this string is greater than n. So its length is n square, right? So we have chosen z equal to 0 raised to power n, and this is the part of this also because its length is a perfect square, right? So what is the next point? By pumping lemma, zero n square may be written as UVW, where modulus of V is greater than 1 and less than or equal to n, and UVIW is in capital L for all I. Right? So we have broken Z into three parts, U, V, W, and we have broken it into by using these two constraints that have been mentioned in the pumping lemma. Next, so that is the major point that we need to change at every step in every example. Contradiction part, where we are choosing the value of I, and when we are putting actually the value of I over here, it will not become the part of capital N. Right. So what we'll do is, in particular, let I equal to 2. We have chosen the value of I equal to 2. However, so now we have put I equal to 2 in UVIW, right? So what is the length of UVW? What is the length of UVW? What is the length of UVW? Which string has been given, which string has been broken into UVW? Z. What is the Z? See the third point. What is Z over here? 0 raised to power n square. What is the length of Z? N square. So it means the length of UVW is n square. Right? So now we have added the component over here UVW plus V. This V square has been broken into two parts. So its length is n square. And this V this has been broken with the condition that the length of V will be in the range of 1 and n. Right? So now what will be the length of UV square W? It will definitely be greater than n square. because the length of UVW itself was n square. So if we are adding it V over here, so its length will be increased from n square. So its length has been increased from n square. So its length is greater than n square first of all, but it is less than or equal to. So the length of V is at the most n. So it means its length can exceed up to n. So the length of V square W lies between n square and n square plus n. Right? Now if we see this n square plus n, it is further less than n square plus 2n plus 1. Is this part less than this part? N square is already there, right? So here it is and it is